Hey, pup.
Hey, Rack.
Hello. We're going to talk about factoring numbers using consistency. The factoring problem is defined like this. Given a product P that has two n bits, find factors A and B that have n bits each. The numbers are represented in binary. We also require that the leading bit of the product lies within the most significant half of the product. This ensures that the factors are not trivially P and 1. Here's an example of successful factoring. In this case, we reverse the vector of bits so that the least significant bit is on the right. If the input vector is 55, then the output vectors will be 5 and 11. Here's an example of a number that cannot be factored because it is prime. If the input is 53, then the output factors will be null to indicate that no factors can be found. Note that this problem is a bit contrived. Since it only converts products with 2n bits into factors with n bits, it cannot factor all products, and it could run faster. However, this problem is easy to explain, and it is easy to fix, if a bit tedious. It also solves many real problems, such as in cryptography. The consistency problem. We're going to implement factoring in terms of consistency. The consistency problem takes three inputs, a number of decisions D, a set of constraints C, and the number of truths T. The goal is to find a vector of decisions with length D that meets the constraints C and that has T truths. Each constraint ij means the decision I and decision j may not both be true at the same time, which means decision I or decision j or both must be false. The consistency algorithm is discussed in other videos in this series. One weird trick. Every chunk of the problem will be mapped into a group of decisions that describes the possibilities for that chunk. Exactly one decision from each group will be marked true, so the number of groups will equal the number of truths. Constraints will forbid incompatible pairs of decisions within groups and between groups. This diagram shows the basic multiply and add box, which is the fundamental group of decisions in the algorithm. It takes bits an and bn, multiplies them together, and adds them into the current running total. Note that an, bn, carry in, and sum in are the only values that affect the state of the box. The carry out and sum out values are functions of the input values. Multiply and add boxes will be depicted by blue rectangles. These are the 16 states that are represented by the multiply and add box. The consistency algorithm will choose exactly one state for each box. Here we show how to use one multiply and add box to compute a 1 by 1 long multiplication. Here we show how to use 4 multiply and add boxes to compute a 2 by 2 long multiplication. Here we show how to use 16 multiply and add boxes to compute a 4 by 4 long multiplication. Each row represents multiplying one bit of the A vector by all of the bits of the B vector, and then all of the resulting rows will be added together to produce the product. This diagram is organized by the position of the bit in the sum. This is the standard long multiplication that everyone learns in school, and variations on this algorithm are also used in hardware multipliers. Here we see the same multiplication matrix, just squared up so that the rows correspond to the bits of the A vector and the columns correspond to the bits of the B vector. The dotted lines show where additional boxes would be added to solve any size problem. The constraints fall into 4 groups. There are factor constraints, carry in and sum in constraints, product constraints, and box constraints. The factor or A and B constraints. These constraints connect the boxes to the A and B factors. The A in values for all of the boxes in each row must be identical, either a 0 or a 1, though the A in values for different rows may differ. Note we don't actually need an A decision for each row. We merely need that all of the ANs in each row be the same. And we don't need all of the ANs for all of the boxes in the row to be equal to each other. We merely need for the ANs in the boxes adjacent to each other to be equal. Then by transitivity, all ANs in the row will equal each other. Likewise, all of the B values in each column must be identical, either a 0 or a 1, though each column may have a different Bn value. And similarly, we don't need a decision to represent the Bn value. We merely need the B values in adjacent boxes to be equal. The carry-in and sum-in constraints. These constraints connect the boxes to each other, and specifically they connect the boxes to the adjacent boxes. In each row, the carry-out of each box must equal the carry-in of the box to the left. In each row, the carry-in of the rightmost box must equal 0. In each diagonal, the sum-in of each box must equal the sum-out of the box above and to the left. In each column, the sum-in of the topmost box must equal 0. And in the leftmost column, the sum-in of each box must equal the carry-out of the box above it. The product constraints. These constraints connect the boxes to the product. Note that the product vector comes from 3 different places in the matrix. And the subscripts for the product are kind of complicated, but they are specific. In the right-hand column, the sum out of the box in row I must equal the product bit I. In the bottom row, the sum out of the box in column I must equal the product bit of I plus n minus 1. The carry out of the lower left cell equals the most significant bit of the product. Note that the bottom right box overlaps because it is both in the right-hand column and the bottom row. The constraints within boxes are as follows. Basically, only one decision within each box may be true, so the algorithm will be forced to choose one. This could be done by adding 120 constraints between all of the different decisions within each box. The number of constraints. Here we show the number of constraints in terms of n, where n is the number of bits in the factors, or 2n is the number of bits in the product. Note that in total there are 632 n squared minus 480 n plus or minus 2 constraints. Because the algorithm creates 16 n squared decisions, there will be slightly fewer than 40 constraints per decision. The decision class describes what each decision means semantically to the factoring algorithm. To the consistency algorithm, all decisions are more or less equal except for which decisions they are inconsistent with. The first 2 values of the class decision are the AID and BID. They identify which bit of the A vector and which bit of the B vector this box corresponds to. All decisions that have the same AID and BID are in the same box. The next 4 fields, left, right, top, and bottom, are shortcut Boolean flags that indicate whether this box lies in the left column, the right column, the top row, or the bottom row of the matrix. The values AN, BN, SUMIN, and CARRYIN identify all of the possible states of the box. 16 decisions correspond to each combination of these values. And the sum out and carry out bits are computed from the AN, BN, sum in, and carry in bits. This is the factor algorithm. The algorithm first creates an array of decisions to spell out explicitly what each decision means. Then the algorithm creates a set of constraints that identify which pairs of decisions are inconsistent with each other. Then the algorithm calls the consistency solve function to actually solve the problem. This returns an array of trues which identifies which decisions are marked true. And finally, if trues is null, then no solution can be found. Otherwise, the algorithm calls makeSolution to convert the array of trues into meaningful factors. We will describe each of these functions in turn. Make decisions. The makeDecisions function creates an array of n by n boxes and each box has 16 decisions, one for each possible combination of AN, BN, SUMIN, and carry-in. The outer two loops enumerate each possible box of AID and BID. The inner four loops identify each possible combination of AN, BN, SUMIN, and carry-in. Inside the loop, it creates a new decision for each one and appends that to the array of decisions, and finally returns the array. The makeConstraints function builds a set of constraints between all pairs of incompatible decisions. It first creates a new set of constraints. Then, for every pair of decisions, it determines whether or not those decisions are consistent. If they are inconsistent, then it creates a new constraint between them and adds the constraint to the set. It finally returns the set of constraints. MakeSolution. First, it creates space for the two factors. Then the function goes through each true bit. If the bit is true, then that decision was chosen. So the AN for that decision will be assigned to the AID for that decision. And the BN for that decision will be assigned to the BID for that decision. Finally, the function will create a solution record from the two factors. The function consistent checks whether the two decisions are the same. If the two decisions are the same, then it checks unary consistency. Otherwise, it checks binary consistency. Unary consistency checks the 5 unary constraints. If the decision is in the right column, it ensures that the carry-in is false. If the decision is in the top row, it ensures that the SUMIN is false. If the decision is in the right column, it ensures that the SUMOUT bit equals the corresponding product bit. If the decision is in the bottom row, it ensures that the SUMOUT bit corresponds to the proper product bit. If the decision is in the bottom left box, then this ensures that the carry-out bit equals the most significant product bit. Binary consistent checks the following 6 constraints. The first constraint ensures that all of the AN values in each row are equal. If D is to the left of E, then D.AN must equal E.AN. The second check ensures that all of the BN values in each column are identical. If D is directly above E, then D.BN must equal E.BN. The third check ensures that carry-in is consistent with carry-out in adjacent cells. If D is to the left of E, then D.carry-in must equal E.carry-out. The fourth constraint ensures that the SUMOUTs are consistent with the SUMINs. If D is above to the left of E, then D.SUMOUT must equal E.SUMIN. The fifth constraint ensures that the carry-out of the left column goes to the SUMIN of the box below. If D is above E and D is on the left, then D.carry-out must equal E.SUMIN. And finally, the last constraint ensures that only one decision within each box may be chosen. So all decisions are incompatible with all other decisions in the same box. So if D and E have the same AN and BN values, then D must equal E. Throughout this video, we may seem to have optimized inconsistently. For example, we optimize the binary constraints, ensuring that the AN values in each row are all equal and that the BN values in each column are all equal. However, there was a method to the madness. We sought to have a linear number of constraints per decision. Beyond that, we avoided optimizing the number of decisions and the number of constraints. And we sought to make the explanation simple. A wide variety of optimizations can be applied to the code in this video. Consider unary constraints. Rather than creating a unary constraint, simply omit the decision. Consider the carry-in and SUMIN constraints. Don't compare each decision to all others, only compare each decision to the decisions in neighboring boxes. Consider box constraints. Don't create box constraints, rather restrict appropriate population cells to 0 or 1. Of course, this needs Hadamard consistency. If we separated the multiply and add boxes into multiply boxes and add boxes, This would reduce the number of decisions per box from 16 to 12, and it would reduce the number of carry-in and sum-in constraints per box from around 512 to about 128, or a factor of 4. Consider the binary and zero constraints. All of them apply to all problems in the exact same way, so they can be precompiled into the data structures. Consider the product constraints. They apply to each problem differently. However, we can restrict appropriate population cells to 0 or 1 when we use Hadamard consistency.